Hello everyone, I'm Paul and today we're solving problem 3495. Minimum operations to make array elements 0. This is a hard one, so we'll go step by step. We're given a 2D array query, so let's say we're given this. Let's say we have only one query. And for each query we have two values, left and right. And this represents an array. In this case, the array goes from 3 to 7. And our job is to return the minimum number of operations required to reduce every element here to 0. For each operation we can take two elements, so let's say we take 3 and 4, and divide each of these by 4. Remember, we are using floor here. So first we are here, the number of operations up to this point is 0. Now we can do one operation, so we divide this by 4, the new value is 0. We do the same here, and the new value is 1. Now we can take these two elements, so we divide this by 4, the new value is 0, and the new value here is 1. Now we have two operations. Now we take these two elements, we divide this by 4, the new value is 0, and the new value here is 1. Now we have three operations. Now we require another operation, so this is 0, this is 1, this is 4. And finally, given that we only have one value, we can take this element and this element, which is already 0, and the new value here is 0, and the new value here is still 0. And given that we require 5 operations to transform every element here into a 0, we just return 5. Now here we only have one query, but we can have up to 10 to the power of 5 queries. And here we only have 5 values for this query, but for each query we can have up to 10 to the power of 9 different values, and this is a very large number. So we can't just build an array for every query and do this simulation and try to get the result in this way, because this will throw TLE, time limit exceeded. So we need to think about something more efficient. So let's start small here. Let's say we take 7 and we are trying to get the total number of operations to reduce this to 0. The base 10 representation of this number is 7. And the base 2 representation, meaning the binary number, is 1, 1, 1. Now remember that this position corresponds to 2 to the power of 0, which is the current position, and we go from right to left. This is 2 to the power of 1, this is 2 to the power of 2. So this is 4, this is 2, this is 1, and 4 plus 2 plus 1 is 7. This is how we go from this binary number to the base 10 representation. Now let's say we're trying to do one operation, so we need to take 7 divided by 4. The result for this is 1. Remember, we always need to round down this value, so the result is 1. Now this is exactly the same as using right shift with this binary representation, and we are shifting these 2 steps to the right. This is as if we remove this and these bits. So the result after one operation is 1 in base 2, which is 1 in base 10 also. So now we have one operation and we start from number 1 and we do another operation. We do 1 divided by 4 and the result for this is 0. And how can we get this in binary? Well, we do the same. We apply right shift 2 times, meaning now we remove this bit. The result in binary is 0, in base 10 is 0, meaning we need 2 operations to transform 7 into a 0. Now let's step back for a moment. Let's say we are here again. This is 7 in binary. Now from here, we know that for each operation we need to use right shift 2 times. So for each operation we remove 2 bits. Now the question is, how many operations do we need to remove 3 bits? Well, we can just take the number of bits that we have here, meaning 3, and divide this by 2. and we need to round up this value. So here we add +1, and the result for this is 2. So with this formula, we have a very efficient approach to get the required number of operations for 7. We know that number is 2. And now we don't have to run every operation one by one. We just use this and we get 2 in this case. And not only that, this formula corresponds to every operation for any number of 3 bits. And how many numbers do we have with 3 bits? Well, we have number 4, which is 100 in binary. We have 5, which is 101. We have 6, which is 110. And we have 7, which is 111. So we know that for all of these numbers, we require 2 operations to make each of these 0. So in total, we need 2 times 4 numbers, 2 times 4 operations, meaning we need 8 operations to transform each of these into a 0. So now we know what is the required number of operations to transform each of these numbers into a 0. And these are individual operations, so we can take 8 divided by 2 and the result is 4. Because remember that for each operation we take 2 values. For example, this and this, this and this, and so on. So the total number of individual operations for each of these numbers is 8. And if we can take pairs, such as the problem describes, the result is 4. So with 4 operations, we can transform all of these into zeros. Now we also need to include 3 in this case, and 3 is not here because it has only 2 bits. This is 3 in binary number. The thing is that we don't have to include every number of 2 bits. We only need 3. So the full approach is the following. This is very similar to prefix sum. We can take the total number of operations required for every number from 1 to the right bound, in this case 7. So the total number of operations to go from 1 to 7 included. And we can subtract the total number of operations to go from 1 to the left bound -1, meaning 1 and 2 in this case. So we take this and we subtract this. This is how we get this range of operations, which is exactly what we want. Now let's say we want to get this range of operations first, meaning operations from 1 to 2. We start from 1, and 1 in binary is 1. And remember the positions. This corresponds to 2 to the power of 0. So we start from here. Remember that the next position here is this times 2, or 2 to the power of 1, meaning 2. 2 to the power of 0 is 1. Next we have 4, 8, and so on. Given that this is 1, this is 0 right now. So now the question is, how many numbers do we have with only this bit? And the answer is, we only have number 1. And we have only 1 bit here. So we do 1 times 1, and the result is 1. Meaning we need only 1 operation to transform this into a 0. So we will have a variable which we'll call operations, and this is initially 0, and now it's 1. And now we can move to this position. So now we take 2 as the base. The binary representation of 2 is 1, 0. And we do the same. We are checking how many numbers do we have with this amount of bits. And the answer is we have 2 and we have 3, which is this in binary. Now the thing is that 3 is out of bounds because we are looking for operations for numbers from 1 to 2 only. And given that this is out of bounds, we only take 2. So given that we only have a 2, we only have 1 number times, and the number of operations is the size for this, 2, plus 1, 3 divided by 2 is 1. So 1 times 1 is 1. So we add this up here, and this is now 2. So now we know that the individual operations for this small range are 2. And we need to do exactly the same with this range. We start from number 1. This has only 1 bit. The amount of numbers with 1 bit is only 1. We only have 1. So we have 1 number times the required amount of operations to transform this into a 0, meaning the size of this plus 1 divided by 2, and the result for this is 1. 1 times 1 is 1, so we add this here, and this is now 1. Now we move to the next base, and this is 1 times 2, or 2 to the power of 1, meaning 2. This in binary is 1, 0, and this has 2 bits. The total amount of numbers with 2 bits is 2. We have number 2 and number 3, which is this. So, given that 3 is smaller than our right bound, in this case 7, we are good to go. We can include every number. So we have 2 numbers, 2 and 3, times the total number of operations to transform this into a 0, meaning the size for this 2 plus 1 divided by 2, and 3 divided by 2 is 1, and 2 times 1 is 2. So we can add these 2 operations. This is now 3. Now we can move to the next base, meaning 2 times 2, or 2 to the power of 2. And this is 4. 4 in binary is 1, 0, 0. Now, how many numbers do we have with 3 bits? Well, let's see. We have 4, 5, which is 101. This is 5. We have 6, which is 110. And we have 7, which is 111. And these 4 numbers are within our range. They are all smaller or equal to 7. So we can include these 4 numbers. So we do 4 numbers times. Remember that the operations in this case are 3, which is the size of this, plus 1 divided by 2. And this is 4 divided by 2. And 4 times 2 is 8. So we add 8 up here, and this is now 11. So the total number of individual operations for this range is 11. And remember, we're trying to get this range of operations, so we can do 11 minus 2, and this is 9. And remember that this number corresponds to individual transformations or individual operations. These are individual operations and these are individual too. And the problem says that for each operation we can do 2 transformations. We can transform 2 numbers. So we can take 9 divided by 2, because for each operation we can do 2 transformations, and we can round up this number like this, and 10 divided by 2 is 5. So finally we return 5. Now, why do we need to round up this value? Well, because for example here we have 5 values. We have an odd number of values, and we don't want to exclude any of these values. We want to include them all. That's why we need to round up this. And here we only have 1 query. Remember, we can have up to 10 to the power of 5 queries. So if we have more than 1 query, we just need to sum all of these results for each query. So this is it for the approach. I know this is a lot, but I recommend you to take this step by step. So now let's go with the code, and hopefully you will get the idea. First we say n is the length of queries. The result is initially 0. And now we can build our function. We will call this operations. And this takes some integer as an argument. And here we always start from base 1. the number of bits is 1 initially, and the number of operations is initially 0. And now we can say while the base is smaller or equal to x, we add 2 operations. And first, remember here we have 2 terms. In this side, we have the total amount of numbers with this amount of bits. We are at some base, and this base, the binary representation for this base, has some amount of bits. Here we are getting the amount of numbers with this amount of bits, and here we are getting the amount of operations to transform these numbers into a 0. So here we take the next base times 2 minus 1, and we subtract the current base and we add 1. This is how we get the amount of numbers with the current amount of bits. Now, it might be a case that this value is larger than x. In this case, it's out of bounds. So in this case, we need to take x as the upper bound. So here we can take the minimum among this and x. And in this side, remember we do bits divided by 2, and we need to round up this. So we do bits plus 1 divided by 2. And now we can move to the next base. So we add 1 bit, base times equals 2. This is how we move to the next base. And finally, we return ops. Now with this function, we can say for left, right inquiries, result plus equal. And remember our drawing, we do operations right minus operations left minus 1 and divided by 2. And remember, we need to round up this value because we might have an odd number of values and we want to include every number. So we add 1 and finally we return result. So this is it for the code. Now let's submit this and see if it works. As you can see, this works and it's very efficient. Here time complexity will be big O of n times log max x, meaning the maximum value in the right bound for any query. Remember that here we have roughly 32 operations as a maximum because the maximum range from left to right is 10 to the power of 9, so that's roughly 32 bits. Remember, we are working with binary numbers here. Now we can work with base 4 numbers instead, and that should make this more efficient. How can we do this? Well, here we start from base 1. Instead of bits, we have base 4 numbers. We'll call this quads. And we initially have 1. This is the same. Here we can move to the next base by doing base times 4. And in this side, we do the same. We are getting the amount of numbers with the same amount of quads, with the current amount of quads. And this is times quads. And here we can remove this because now we are working with base 4 numbers. And here we can add 1. And we move to the next base with times 4. So this should be a little bit more efficient and it's basically the same. As you can see, this also works and it's more efficient than the previous solution because basically we are working with base 4 numbers here. And we do the same. We take the amount of numbers with the current amount of quads. I guess we can call this quads instead of bits, and we multiply this by the required operations to make these numbers 0. And this is overall more efficient because here we have at most 16 operations instead of 32. So this is it for this problem. If you found this useful, please drop a like, subscribe, and see you in the next one. Bye bye.